electrolysis, we're just going to talk about a few points from acids and alkalis, which we need to just quickly recap over, and then we can move on to electrolysis. So the first thing is the diagram on top here showing the color variations with universal indicator and various substances. You must know the pH value for at least one or two items that have been listed here. You may be asked in an examination question to fill in a table suggesting a possible product for a particular pH value or color. So it's important that you know a corresponding, let's say, substance for a pH value and universal indicator solution. This shouldn't be new to you. You would have come across this in previous years, the pH scale and its universal indicator, corresponding universal indicator solution color. Here you've got a few items that you can actually put towards those pH values and color variations. So just make a note of that if this is something that you are not confident with. Now moving on to the table below. Now this is showing the concentration of H plus ions and its corresponding pH value. I want you to study this table, and I want you to just quickly pick up on the pattern that's emerging as we either increase or decrease the concentration, let's say by a factor of 10. What is happening to the pH value? If you could just pick up on a pattern here. So just pause the video, study that table, and see if you can pick up on a pattern that's emerging as the pH value increases. So what you should find is that as you decrease the concentration of H plus ions by a factor of 10, you increase the pH by 1 unit, by a value of 1. So from pH 1 to pH 2, we are decreasing the pH by a factor of 10. So magnitude, of 10 is decreasing as we go from 0.1 to 0.01. And what does that do to the corresponding pH value? It increases it by 1. And the same from pH 2 to pH 3. So let's just put this in a concise way, just one sentence to the side. So what we say is that decreasing the concentration, or let's say decreasing the H plus ion, decreasing the H plus ion concentration increases, decreasing the H plus ion concentration by a factor of 10 will increase the pH by 1. Okay, so what we're saying is that we can also look at it in the reverse way as well. We can say that as the concentration of H plus ions increase by a factor of 10, the pH value decreases by 1. So it doesn't matter which way you look at it, as long as you understand that there's an order of magnitude here that we're looking at, and that it affects the pH value, and we're looking at an order, and this is by an order of this is by one order of magnitude, so an order of magnitude. Okay, so if we increase it by an order of magnitude, the concentration, if we increase or decrease it, this has a corresponding impact on the pH value. So I'll repeat in a summarized way. If we decrease the concentration of H plus, and remember we're looking at the H plus, so pH is affected by the H plus ion. If we decrease the H plus ion concentration by a factor of 10, i.e. an order of magnitude, we will increase the pH by 1 unit. Look at it from another point of view. If you increase the H plus ion concentration by a factor of 10, you will correspondingly decrease the pH by 1 unit. So let's just put 1 unit there to make it so we don't confuse it with pH1. This is 1 unit. Okay, so just be aware of that. So can you pause the video here and just quickly put a summary sentence, a couple of sentences explaining the relationship between the concentration of H plus ions and the pH value. So I want you to pause the video now. You can take down the definition I've written down, but I rather you, from what we've just talked about, put it in your own words. A couple of sentences that will describe the concentration of H plus ions linked to pH value, and use that table to help you. I'm going to give you a series of concentration values for the H plus ions. I want you to then tell me what the pH value would be for each concentration that I give here. So I'm going to give you a concentration value, and I want you to be able to tell me the corresponding pH value. Okay, so we'll keep it there, we'll just hold it there. So can you, for these concentration values, can you give the corresponding pH? So can you find out the corresponding pH for these concentration values of H plus ion? So just pause the video here, quickly sketch the table out, and then I want you to give me the corresponding pH values for the concentration of H plus ions indicated here. Okay, so let's take a look now. So what you should have is that, so let's say for the first one, you should have a value of pH 8. So let's say our pH 8, put it here, so we'll say, let's not write pH 8, let's just write 8 here. Okay, so we've got 8 there. Then you should have, for the third one, I'm going to do this quickly, then we're going to talk about how we got these values. Let's make it a little bit darker. Okay, so what you can see here, a series of pH values that have been given for the corresponding concentration of H plus ions that are indicated on the table. Now, this is how we're expressing the concentration values in standard form. And those of you that are good at maths would have picked up what was going on here. And what you can do is to make it easier for you. So let's say you're given a standard form value and you're struggling to find out what the pH is of the concentration. So what you can do is that when it's represented in this way, you may have noticed that the power, if you take the minus power value to which 10 is raised to, it gives you the pH value. For example, if you were to take this, let's put it in another color, it's not clear. Okay, let's take a color we haven't used. Okay, if you were to take 8, you can see it's pH 8. If you were to take 2, you can see it becomes pH 2. So what you're seeing is another way to represent the concentration values. This is in standard format, and you can see that the pH value, how to actually pick out the pH value from the concentration. So just be aware that this is another way. Generally, exam questions will not be at GCSE to this extent. However, if you're given a concentration value represented in standard form, do not get phased by this. It's not a difficult way to deconstruct and figure out what the pH value is. So just take a note of this to know that, to reinforce the idea of how we get pH values, and this is just another way in which it may be represented to you. So it looks more complicated than it is. It's quite simple to actually deconstruct. So take this table down and make sure that you can see that the corresponding pH and how it aligns to the standard form format. We are going to look at electrolysis, and we're going to explore the process of electrolysis. That's the first step we're going to look at. So we're going to define what electrolysis is and look at the overall procedure of how we actually utilize electricity in obtaining a certain product. And the second part is that we're going to look at and explain. You should be able to explain why electrolysis will work on certain compounds and these specific compounds, and why they work on these compounds, i.e. salt compounds, but not on other types of compounds. So you need to be able to explain, and certain exam questions do tend to repeatedly ask this. It comes up almost every year or every other year about why electrolysis works in this particular compound, and explain what needs to happen for electrolysis to occur. So there's an explanation in terms of why electrolysis proceeds the way it does for certain compounds, and we need to be comfortable in that explanation. So that will be the second part. So the first part, we will just look at an overview of electrolysis, the mechanisms of electrolysis, the setup of it, and then we'll look at the explanation as to why electrolysis works for certain compounds and why we're able to use it for certain compounds. Define the word electrolysis. So when we look at the word carefully, electrolysis, we can see that it's in part the same as another word, and that is hydrolysis. We came across the word hydrolysis where we were using water to split apart a substance. And in this case, we are going to use electricity to break apart a substance, or to break down a substance. Now, so the lysis part, the breaking down part, is, we've established that. Now, the second part of the word electro, so it's electricity, using electricity to break down a substance. Now, because we're using an electric current, there are certain compounds that we can use electrolysis on, and these are ionic compounds. So can you write down using electricity, okay, to break down ionic compounds. Okay, so in electrolysis, we're using electricity to break down ionic compounds. And specifically, if you want to be more precise, we're using an electric current. So we've defined that electrolysis is the breaking down of an ionic compound via electricity. Now, another way in which we can phrase the ionic compound part of the definition is to call the compound that is being broken down via electrolysis as an electrolyte. So we say the compound broken down via electrolysis is known as an electrolyte, or as the electrolyte. Okay. So as this topic is electrolysis, you have got here a copper wire, a section of copper wire, and we're looking at it at the atomic level. Now, I want you to tell me how electricity is being conducted here in this metal copper wire. Use the diagram to help you. So pause the video, and can you just write down a 2-sentence answer, 2 to 3 sentences, just explain how electricity is conducted in this metal wire. Okay, so what you should have got on your answer is that the electrical energy can be carried from one region of the copper wire to another because of the free electron clouds, the delocalized electrons, which are found in the metal. And you can see they group together in certain regions in more concentration, but the main point is that they're free delocalized electrons which are able to move to some extent. Now, this means it's not that the molecules are held in a fixed position, the electrons are held in a fixed position. They are able to move and they're free. Okay, so due to the free electron cloud or free delocalized electrons within the metal, electrical energy is able to be carried through the region of the metal wire, through different regions of the metal wire. So that's how electricity can be conducted or carried. The electrical energy can flow through the metal. Now, why have I shown you this image here and asked you to write a definition for this? Okay, so I'm going to show you another image now of an ionic compound. And electrolysis, as we looked at our definition, is the breaking down of an ionic compound using electricity. But I'm going to show you an image now of an ionic compound, and I want you to tell me how this ionic compound will conduct electricity. So here you can see solid sodium chloride. Now, what I want you to do is to pause the video here. After studying this diagram, I want you to tell me how this ionic compound is going to conduct electricity. So just think about it. Refer back to the previous diagram where we were looking at the flow of electricity in copper wire, and try and see if you can come up with an explanation as to how this ionic compound is going to be used in electrolysis. and only use the diagram that you have here. And whatever is being said here regarding this sodium chloride compound, i.e. solid state, that's the only hint I'm going to give you. So how is this solid state sodium chloride going to conduct electricity for electrolysis to occur? All right, okay, so what you should have realized quite quickly is that though we need an ionic compound for electrolysis to work, based on our definition, the ionic compound in this state is not going to be able to conduct electricity. Though this compound is made up of positive and negative ions, it's not able to conduct electricity in this solid state because none of the ions are free to move. They're all held in fixed positions. Yes, there is some movement here because in a solid, though the atoms are held in fixed positions, there is still vibration. Nothing technically in the universe is at a stationary point. Everything is moving, whether it's a relative movement or even if we go a relative movement in terms of large objects, something is always moving in relative, let's say there's always relative movement in terms of large objects to each other. If we go down to the molecular level, there's also movement, and when we go down to the atomic level of solids, there's also movement in terms of the particles are vibrating. In certain instances, there can be a situation where we can get to a point where there is no movement, but these are not needed at this stage. And what we generally say, the general accepted theory is that everything is moving in one form or the other, whether it's vibration on the spot or whether it's relative movement. But the point we're trying to make here is that ionic compounds can only be electrolyzed when they are molten or dissolved in water, simply because in a solid state, the particles, the ions, are held in fixed positions due to strong electrostatic forces. So this is a type of exam question that does tend to come up a lot, asking why, let's say, solid sodium chloride cannot be electrolyzed when the sample is in this condition. And if it's in a solid state, you have to say that due to the strong electrostatic forces of attraction between the ions, the electric charge on the charge cannot be carried, and you cannot have a complete circuit because the ions are not free to move, and the charge cannot be carried through to complete the circuit. Let us now put that into a few sentences. So can you take down electrolysis can only be carried out on molten or aqueous ionic compounds. Okay, so this is an important statement because it's one of the crucial points or aspects of electrolysis, that it can only be carried out on molten or aqueous ionic compounds. So can you just underline the words molten and aqueous? Okay. Now, this is because their ions are free in these states, molten or aqueous, to move and carry their charge to the electrodes. So can you just write this down, please? This is because in molten, I'm going to put the state symbol here, okay, which I'll put in a different color just to emphasize. In case you see this in ionic half equations, it will come important as well. So molten is L. Let's make it a bit more clear. So molten is L, okay. So this is because in molten or aqueous, states, and let's put that blue again. This is because in molten or aqueous states, the ions are free to move. Okay, the ions are free to move and carry their charge to the electrodes. All right, so this is why it's important to have a molten or aqueous state for the ionic compounds. Ionic compounds tend to be crystalline in structure in a solid state. We have to make them molten or dissolve them in water, making them aqueous, and this will free up the ions and allow them to carry their charge to the electrodes and thereby splitting up this ionic substance. And this is the process of electrolysis. Here you can see the process of electrolysis where you have free ions. Notice that they are free to move, and because of this free movement we are able to split apart this ionic compound. And ions simply mean a particle with charge, and here we've got our positive and negative ions, and the electrodes will complete the circuit. And we're going to talk about these electrodes in terms of their relationship to the electrical circuit for electrolysis in a moment. But the importance of having free ions for electrolysis to occur is represented here. Why do we need free ions? For this process to happen, what you're seeing in front of you. And this is the process of electrolysis in a nutshell. There are different types of ions. There are more than 2 types of ions here, not just your standard positive and negative ion. There are extra negative ions as well. So when we actually perform electrolysis, you can have more than 2 types of ions that are being attracted to the electrodes. So just be aware of that. And when we complete certain ionic equations, this will also be important to remember, that it's not just necessarily 2 ions in the solution. If it's an aqueous solution, there's likely to be more than 1 type of positive ion or negative ion. So just be aware of that. And you can see that represented in this simulation here. I'm simply showing the circuit just with the electrodes and a cell. Now, what you generally have to remember is that the electrodes are made up of unreactive substances, highly unreactive substances or inert substances. And what we can use for the electrodes, they can be made of carbon graphite, okay, or let's say an expensive metal like platinum. Now what I want you to do is to pause the video here, and a quick question, and I want you to attempt this question, is to tell me why are we wanting to use inert substances such as carbon graphite or platinum. And platinum is a metal. So why do we use these substances, and why do they have to be inert? Why couldn't we use an inert substance such as wood, for example, or plastic? Why are we using an inert substance, and then also why are we using specifically inert substances? Okay, so first of all, because we are dealing with an electrical circuit, we are eventually going to have to complete this circuit. This circuit is not complete right now because we don't have a solution. So what you're going to see soon is that this would be in an electrolyte solution, and then we will have our charges to complete the circuit, and the charges can flow. But as now, we don't have a complete circuit. However, that is our goal, to have a complete circuit. If that is the case, the elements that make up the electrodes must be able to conduct electricity. Carbon graphite will conduct electricity. And platinum, being a metal, will also conduct electricity. Now, what you also need to understand is that we use an inert substance such as graphite, carbon graphite or platinum because they're very unreactive. This is because we do not want any side reactions happening with the electrolyte, or we don't want any reactions to occur once the product is formed at the positive or negative electrode, because the build-up of these charges is our product on the positive or negative electrode, and we don't want side reactions happening when the product is formed, and we don't want side reactions happening when there is a molten state electrolyte or an aqueous solution. So for that reason, we use inert or unreactive substances. Here you can see the electrolysis experiment set up in its complete form here. Notice that the beaker and the electrolyte, in this case it's molten lead bromide, complete the circuit. And this is the complete setup for the process of electrolysis, and in this case it's getting lead and bromine from electrolysis of molten lead bromide. And notice that the electrodes are attracting the ions of lead and bromine. And we're going to talk about the positive ions, how they're attracted to the negative electrode, and the negative ions are attracted to the positive electrode. But what I want you to do is, for now, pause the video, and can you so your task is just to draw out a quick experimental setup of electrolysis, and in this simplified format. So task. Okay, so what I want you to do is to take 5 minutes. Okay, and can you sketch this? Can you sketch this diagram, the complete electrolysis diagram, and can you just sketch it out and label it as you see it here? Okay, and notice that you need a complete circuit. Okay, so if you had any breaks in the circuit, i.e. you did not have an electrolyte solution, or you did not have the electrolyte in its molten state, then you would have an incomplete circuit. So just be aware of that. Under your diagram, I want you to take down these statements. Cathode. So cathode, Okay, now cathode, this is negatively charged. Negative charge. Okay, so I'm just going to give you a few points about the cathode. Negatively charged electrode. Okay, that's the first point. And second point is positively charged ions will move towards it. So can you just write down positively charged ions will move towards it. Okay, so the cathode is negatively charged and positively charged ions will move towards it. So the positively charged ions in the electrolyte solution or the molten electrolyte state, whatever is positively charged in that container is going to move towards the cathode. Why? Because the cathode is negatively charged. So can we underline? Can we underline here? Cathode is negatively charged, and it's important that you remember that. It's negatively charged, and positively charged ions, so positive ions will move towards it. So just make sure you understand the distinction here. Cathode, negatively charged. This means anything positively charged in the electrolyte solution is going to move towards the cathode. The cathode is negatively charged, and positive charged ions are going to be attracted towards the negatively charged cathode. We have to also be able to explain this reaction that happens at the cathode in terms of oxidation and reduction. So I'm going to explain this later on towards the end of the video, but can you just put this point down? Reduction occurs at the cathode. Okay, we're going to talk about this in terms of ionic half equations later on, but we've already looked at oxidation and reduction in terms of oil rig, where oxidation is loss of electrons and reduction is a gain of electrons. I'm just going to leave it here, but keep this in the back of your mind that we are going to have to start talking about reduction and oxidation in terms of electron gain or electron loss. But I'm putting this statement here so it's in your notes that when you revise, you remember that reduction occurs at the cathode. Okay, so reduction occurs here. And as a side note, if you just recall back to our previous lesson, reduction is gain of electrons. So now we come to the anode, and the anode is the positive electrode. So can you write down this bullet point? It is the positive electrode. Okay, if it's the positive electrode, it means that negative ions are going to move towards it. So will attract negative ions. Will attract negative ions from the electrolyte. Okay, so negative ions are going to be attracted towards the positive anode electrode. This means in terms of oxidation and reduction, we say that oxidation, so can you just write down underneath that? Oxidation occurs at the anode. So it is important, as I said, we'll come on to this later in terms of electron gain and electron loss for ionic half equations. And you need to remember that oxidation occurs at the anode. We've just discussed in terms of cathode and anode. On your diagram now that you should have in front of you, on your piece of paper in your notes, can you now annotate your diagram to identify the cathode and the anode here on the diagram? Because that name, the names cathode and anode were not given here. But now we've gone through the definition for cathode and anode, can you identify the electrode that is the cathode, and can you identify the electrode that is the anode on this diagram? I'm not going to put the answer here. If you struggle on this, can you tell me on Teams, and can you ask me that question on Teams? I just want to see how many of you are getting this and how many of you are struggling with this. So if you struggle with this, can you ask me on Teams for the correct answer here? The ions reach the electrodes. They will either gain or lose electrons, and subsequently they will lose their charge. So regardless of the electrode that the ions are navigating to or migrating to, once they reach those electrodes, they will lose their charge and they will become either atoms or molecules of elements. So can we take this down? When the ions, let's say migrate to the electrodes, and lose their charge. So the ions migrate to the electrodes and lose their charge. They become atoms. Now this is important. When an ion gains or loses an electron, whichever happens, whether it's oxidation or reduction, once the outer shell of the valence shell has been taken care of to give a whole atom, then it stops being an ion. So once the ion has lost its charge, it may have gained an electron in the valence shell, it may have lost an electron in the valence shell. Whichever one has happened, it stops being an ion and becomes an atom. In some cases, the ions form molecules. They become atoms or molecules of elements. So an element is formed at the electrodes, and they can be atoms or they can be molecules. For example, if we look at the diagram that you see on the right hand side, you can see chlorine gas is being formed. So chlorine exists in a diatomic state. Chlorine exists in a diatomic state, Cl2. So that's a molecule. And zinc metal is different from chlorine gas because zinc is a solid. So that's another way in which the ions, once they migrate to the electrodes, they may change in terms of the state, for example chlorine gas, and then you've got zinc metal, which is a solid. So we say that once the ions migrate to the electrodes, they become atoms or molecules of elements. Experiment can be seen on the right hand side, so the diagram that we've just seen. Now just to note that the observation of this investigation can be described in a way where you can observe a pale green gas being given off, which is chlorine gas. So just note that this is a pale green gas. Okay, so if you're asked for an observation for the electrolysis of zinc chloride, you should be confident to say there's a pale green gas being given off, since chlorine, Cl2, is formed at the positive electrode. Okay, so let's describe what's happening in regards to zinc chloride when we perform electrolysis in this solution. So, sorry, not solution, in the molten state. So, when electrolysis of zinc chloride occurs, when we look at the ions, we can see in this diagram on the left hand side that zinc 2 plus moves to the cathode, which is negative, and Cl minus, the chlorine ion, moves to the anode, which is positive. Now, before we get on to the ionic equations, let's first put down a word equation that sums up this. So now let's put this word equation for the electrolysis of zinc chloride down. So we have zinc chloride goes to zinc plus chlorine. Now let's look at the symbol equation. Now this symbol equation is not complete. I've intentionally left out the state symbols in this equation. Now, this electrolysis reaction does not occur in an aqueous solution. So, knowing that this electrolysis of zinc chloride does not occur in an aqueous solution, could you now pause the video and correctly fill in the state symbols for this electrolysis? And what is happening in the products is what occurs at the electrodes. So knowing that, could you now pause the video and correctly fill in the state symbols for this equation? Okay, the state symbols should be this. Zinc chloride, since we are performing electrolysis and we have stated that it's not an aqueous solution, zinc chloride must be molten then. So we put L here. L represents molten. And since zinc has been formed, zinc is a solid metal once it goes to the cathode, and it will form in small clumps. So we say this is a solid here. It sometimes can be in between a solid and a liquid. However, we say solid zinc forms due to it not being an ion anymore. and chlorine at the electrode becomes a gas. Chlorine is a gas, a diatomic molecule. So that is the state symbols for the reaction, and it's important that you understand and you should be able to explain these state symbols. So here we have the full equation for zinc chloride, the electrolysis of zinc chloride. I'm going to give you an ionic half equation for the formation of zinc. And I want you to see how I am constructing this ionic half equation for the formation of zinc metal. Now, looking at this equation, which is the ionic half equation, you can see that the zinc 2 plus ion, which is also represented in the diagram, goes over to the cathode, which is negative, and picks up 2 electrons. Therefore, it loses its charge because plus 2, when you add it to something that's 2 negative, you're going to cancel it out. So now it becomes a zinc metal. So our zinc metal has been formed. So zinc metal is formed at the negative electrode or at the cathode. Now look at the anode. I'm going to give you the ionic half equation for the formation of chlorine gas. However, it's not complete. I want you to look at the ionic half equation and balance it. So, now look at this ionic half equation carefully for chlorine. Looking at that, I want you to balance that equation. So just pause the video here, quickly write down the full equation, the ionic half equation for zinc, and then write the ionic half equation for chlorine, the formation of chlorine gas, but I want you to balance it because this equation is not balanced. So could you just balance this equation? So pause the video and balance the equation, the ionic half equation for chlorine. Okay, you should have a 2 there. So now this is the ionic half equation in a balanced, that has been balanced fully for chlorine gas. Now what is happening with the chlorine ion? Chlorine gas is being formed at the anode because the Cl minus ions are migrating towards the anode because of the force of attract, because of the opposite charges which are attracting each other. And there the chlorine ions are losing 2 electrons, and thus they're forming their diatomic molecule of chlorine gas. This is because when we have at the electrode, we are having oxidation. So at the anode, oxidation is taking place. Oxidation is loss of electrons. And at the cathode, we are having reduction, which is gain of electrons. If we look here carefully at our ionic half equations, we can see this being represented. This first equation for zinc, if you look at it, we are adding together. if you look at this part of the equation, we are adding 2 electrons to zinc 2 plus. So it's gaining electrons. Therefore, we say the ionic half equation for zinc at the cathode is a reduction reaction. So we say here it is reduction. It's a reduction reaction, or we say that the zinc has been reduced. So let's put it in another way in which you can say zinc has been, I'm going to run out of space, reduced. So for this one, zinc has been reduced. Now, if you look at chlorine, because the chlorine has lost 2 electrons, because if you focus here, you can see that chlorine has, in one sense, got rid of 2 electrons, and you see it separated from it towards the product side of the ionic half equation. So chlorine has lost electrons. Loss of electrons is oxidation. Now, if you're forgetting what is reduction, what is oxidation, always remember this. And we looked at this in a previous lesson where we had this quick 2 words to remind us of how to actually view oxidation reduction. Oxidation is loss of electrons. Reduction is gain of electrons. So the chlorine has been oxidized. So we say chlorine ions, or chlorine has been oxidized. So oxidation has occurred at the anode to form chlorine gas. Reduction has occurred at the cathode to form zinc metal. So let us now put a few sentences describing the ionic half equations you are seeing. So what we say is that for zinc ions gain electrons. Zinc ions gain electrons, and this is known as a reduction reaction. So reduction has occurred here. So zinc ions gain electrons to form zinc atoms. Notice the difference. Zinc ions, zinc atoms. Okay, and this is essentially by forming the zinc atoms, you are forming zinc element. Okay, so that is for zinc. Now, what about chlorine? Let's put it in a different color. Okay, so for chlorine, what we say is that chlorine ions lose electrons. Okay, so chlorine ions lose electrons, and this is an oxidation reaction. Okay, so oxidation has occurred. So chlorine ions lose electrons to form chlorine atoms. And specifically, we have to go a bit further here. We say the chlorine atoms combine to form molecules of chlorine gas. So we just have to put an extra sentence there because we have a diatomic molecule. When we have chlorine gas, we say the chlorine atoms combine to form molecules of chlorine gas. Because chlorine gas, chlorine is Cl2, just remember that, it's diatomic. So zinc ions gain electrons by process of reduction to form zinc atoms, which is a zinc metal. Chlorine ions lose electrons by process of oxidation to form chlorine atoms. The chlorine atoms combine to form molecules of chlorine gas. Why? Because chlorine is a diatomic molecule. It does not exist in its singular atoms. It does not exist as singular atoms. For this task, I'm going to give you, let's say, 6 minutes should be enough. Let's say 6 minutes. So I'm going to give you some ionic half equations, and I want you to balance them. So I want you to write them out fully, and I want you to balance them. So the first one, second one, third one, I'm going to make this one a bit harder. Okay, I'm going to just give you this one. Okay, so the third one, I've left out something. So it's not a case of balancing, it's a case of actually completing it fully and balancing it. So can you just pause the video here? Can you write out these 3 ionic half equations and balance and complete them as fully as possible? Don't worry about state symbols right now. I just want you to be able to balance these equations, ionic half equations, fully, or complete them fully and balance them. Okay, so your answers should be Al3 plus means that we need to have a 3 here, because that's the only way that we will balance the three positive charges to give us a neutral aluminium atom. So we have 3 plus on the iron side, so we need to add 3 electrons to balance out the charges and give us a neutral atom. Question number 2. We start with O2 minus. All right, here we have O2 minus ion. Now we need to get a diatomic O2 molecule which is neutral, and straight away we can see that we have 2 atoms. Okay, so here if we look at this part of the equation, we have 2 oxygens. Therefore, we need a coefficient of 2 here to make it balanced in terms of how many oxygen ions we have in relation to oxygen atoms. Now we need to take into account the electrons. So we are going from, according to this section of the equation, we have got -4 in total, because two oxygen ions, each having a charge of -2, is going to give us a total of -4. Therefore, for us to get a diatomic neutral oxygen molecule, we need 4 electrons to come off. So we say 4 as a coefficient for the electrons at the product side of the ionic half equation. And now this is fully balanced. Now moving on to question number 3. Now question number 3, I made it a bit more difficult because I left out the electrons completely. I wanted you to figure that one out. And what you should have got is this will give you a full balanced ionic half equation for calcium. Ca2 plus, if it's going to if it's a Ca2 plus ion going to a calcium atom, this must mean that 2 electrons were needed to be added to balance out this positive 2 charge, and so we needed 2e minus put here on the left hand side. Now for each equation, I want you to pause the video here and write down whether it's an oxidation or reduction reaction occurring. So whether it's an oxidation or reduction reaction that's occurring and where it would be occurring. So which electrode would it be occurring at? So just pause the video, couple of minutes, think about it. Is it an oxidation reaction or a reduction reaction for each one? And which electrode would these reactions be taking place at? Okay, so let's take a look at the answers. First one, aluminium has gained electrons. So this is a reduction reaction, and reduction reaction is going to happen at the cathode. Okay, because cathodes are negative, therefore the positive aluminium ions are going to be attracted there. Okay, now number 2, we have O2 minus, which is a negative ion, and it has lost 4 electrons to give us a diatomic O2 molecule. So if it's lost electrons, we say this is an oxidation reaction. Okay, and oxidation reactions happen at the anode. Anode is positively charged, therefore negative ions are going to be attracted there. Question number 3, we have a positive Ca2 plus ion, calcium 2 plus ion, and so let's just work it backwards. If we have a calcium 2 plus ion, a positive ions are going to be attracted to the cathode, which is negative, and if we've started with a positive ion and we go to a neutral atom, that means we must have gained electrons to balance out the positive charge. So this must be a reduction reaction. So you see how you should be confident in determining where oxidation has occurred, where reduction has occurred, and where the reaction is taking place in terms of the electrode. For this reaction, lead bromide, I've given you the full equation with the correct state symbols, and what I want you to do is to look at that equation. I just have to amend something here. That's 2. Look at that full equation, and I want you to write 2 ionic half equations, okay, for the reactions happening at the cathode and anode. So listen to what I'm saying carefully. I would like 2 ionic half equations, okay, one ionic half equation happening at the anode and the ionic half equation representing what's happening at the cathode. I've given you a diagram to help you, and I've given you the full symbol equation. I want you to give me 2 ionic half equations representing the electrolysis of lead bromide. That's the first thing, and the equations must be fully balanced. Then I want you to give me a sentence describing, in terms of oxidation and reduction, what is happening to the lead ions and the bromine ions. So pause the video here and take 5 minutes. It shouldn't take you the full 5 minutes. You should be able to do this under 5 minutes. State the 2 ionic half equations fully balanced and state what is happening in terms of oxidation and reduction at the cathode or the anode regarding the lead ions and the bromine ions. Okay, so let's take the ionic half equations. So the 2 ionic half equations you should have are, the first one, you should have lead 2 plus. You could have got this from the diagram. Let's put this in a bit. Lead 2 plus. This plus 2 electrons. Okay, because we have a 2 plus charge, we need 2 electrons, gives us lead metal. That's the first ionic half equation. The second ionic half equation, we've got bromine ion, okay, and we are getting bromine. Now remember, this is where you have to use the equation, the full equation, to help you. Bromine is a diatomic molecule, and you can see it represented there. So bromine has become Br2, which is diatomic. So this equation is telling us we have 2 atoms of bromine. Therefore, we need a coefficient of 2 here. And therefore, we need to plus 2 electrons need to be here. If bromine is starting with Br minus and we have a coefficient of 2, therefore we need to take out two electrons to give us Br2, a diatomic neutral molecule. Now, what is happening in terms of oxidation and reduction. How can we say what is happening? So what we say is that, so let's tackle the lead first. Lead ions gain electrons. Okay, lead ions gain electrons, therefore this is a reduction reaction. Lead ions gain electrons, therefore it's a reduction reaction, and they gain the electrons at the cathode. So lead ions gain electrons via process of reduction at the cathode, forming lead atoms. Okay, so that's for lead ions. Now, what about the bromine ions? So we say bromine ions lose electrons, oxidation to form bromine atoms, and this happens at the anode. So we say bromine ions lose electrons, and this is oxidation, okay, at the anode, forming, and I'm just going to combine the two steps of atoms going to molecules. I'm just going to say at the anode, forming diatomic bromine molecules, okay, which is in a gaseous state. So you should be getting a good idea of how to look at ionic half equations and explain them in terms of oxidation and reduction and cathode and anode. Okay, so for the final part of the lesson, I've given you 3 different types of electrolysis reactions here. One is for molten sodium chloride, the other is molten potassium chloride, and finally molten magnesium chloride. What I want you to do is, using the same format we've had for lead bromide, I want you to give me 2 ionic half equations for each reaction, and also explain what is being reduced, what is being oxidized, and where this is happening in terms of cathode and anode. So be precise in terms of where it is happening. Also, check to see if all the equations are fully balanced in terms of the equations I've given you. So the equations I've given you for all 3 reactions, check fully to see if they're all balanced, and if they're all balanced, then proceed to give me 2 fully balanced ionic half equations for each reaction, and then proceed to tell me where oxidation is occurring and where reduction is occurring. Now I want you to complete this and post it back to me on Teams. So I'll give you 15 minutes for this. You can finish it in class. If not, it will be homework. So I'm expecting you to complete this and post it back to me on Teams. If you can't do it within this lesson or today, I'm expecting it to be handed in before the next lesson, before our next chemistry lesson.